friends. This is Wednesday, September the 3rd at about 7:30 Central or so, the vBrownbag US edition. Tonight we're going to have on Mr. Jeff Carrell talking to us about IPv6 in all of its various wonderful things. Before we get started, we do a little bit in the way of logistics. This quick note slide has gotten bigger and bigger and bigger over time. Basically, we have a lot of stuff going. If you're going to be at the OpenStack Summit in Paris and want to do a lightning talk or a tech talk or basically anything that's about 15 minutes or so, open topic, the vBrownbags will be there handling the lightning talks for the OpenStack Foundation again. We did this in Atlanta. It was really, really successful, and we're hoping to do the same in Paris. Same thing goes if you're going to be at VMworld in Barcelona. We're doing the same sort of thing. The sign-up sheets are at the corresponding websites there, professionalvmware.com or openstack.provtolv.com. We do try to manage chat both through the GoToWebinar client as well as online. In addition, for those of you playing along at home or in the recording, we monitor the vBrownbag hashtag as well as it looks like we're up to 4, maybe 5 Twitter handles now. So another thing that's just grown wonderfully in my absence. We also have a number of different podcasts. We have the Asia Pacific, which goes every other Thursday. EMEA, which is Tuesday nights at 7 p.m. Latin America, which is at 7 p.m. Pacific. And, of course, tonight, Wednesday at 7:30 Central. Our guest tonight, again, is Mr. Jeff Carrell. I'm Cody Bunch, and we also have a co-host on tonight, Ahmad.
Yes, sir.
Okay. So with that, let's see if we can change presenter to Jeff the panelist, not Jeff the viewer. Boom. And in a couple of seconds, his screen should come up. I didn't screw that up too badly, anyways.
Nope, we're working on it. It should be shifting. It's clicking over now.
All right. Well, I see your screen. If you want to tell us a little bit about who you are, what we're talking about, and just dive right in.
Well, awesome. Thank you very much for the invite. It's kind of exciting to be on this podcast tonight. Again, I'm Jeff Carrell. I am out in Fort Worth, Texas, and I'm a network guy, not a server guy, which kind of puts me in an interesting place where we're at, but I've learned a little bit about server stuff, as one might say. I've been in networking a long time. First built my network in 1986, been playing in computers since 1979, so been doing a lot of different things. And I lit upon IPv6 about 4.5 years ago on a project and just decided that that was the coolest thing that happened in technology for the rest of my life. And so tonight we're going to be talking about IPv6 from a kind of a basics perspective and trying to draw a lot of parallels for folks that know IPv4 and are trying to get a handle on IPv6, because there's a lot of things that are similar from a naming type convention, and then there's almost 50% of it that's called something different or operates a little bit differently. So my goal is to help bring those bits of information together for everybody. Anything else on that?
Will you also touch on what happened to IPv5?
Well, IPv5 had a very limited run. It was a multicast, a very special multicast protocol that was assigned, and that was it. So it actually had been given an assignment, never really used or deployed or implemented anywhere, and so they, quote unquote, had to go to the next number. And I'm going to talk a little bit about, not that, but a little bit about V6 history.
That's interesting. I didn't actually, like, I thought, I was expecting you to tell me, you know, like the unicorn god came down and ate it and just shat out IPv6, right? Like, I would have believed anything. So.
No, it's real stuff. It actually is an assigned protocol, but like I say, it just never got implemented, never got used. Many other things changed, and so they, like everything else, once it's an assigned deal, it's got to be, you know, go to the next one on the list. I don't know. I'm not good enough to make up stories like that. Next time I'll try harder, I guess.
No worries.
So I guess we're ready to get started into this.
It's up to you. If you're ready, I'm ready.
I have 5 hours of material to do in an hour and a half. So for everybody that's here, welcome. Thank you for taking time out of your night or your day or your late morning or whatever time frame you're in. In North America, it's just after dinner time for quite a few people. But do appreciate you taking your time out, and again, the Virtual Brown Bag team for letting me come in and play. So V6, I've got a number of different things, and we're going to move relatively fast, but it's one of those, you can't do it in 5 or 6 slides. But, you know, if you do, you're not really giving any good technical information, and my goal is to give you more technical, real world, at least you hear it once, and then as you start down your IPv6 learning path, the seeing it again, hearing it again, playing with it again might make a little bit more sense. I don't get to see how many people we have here, but I would say hopefully some folks have maybe started playing with V6, and if you haven't, that's totally fine. So you can kind of see, we're going to just start out, talk about different components about V6, kind of move up into various other topics. There's not a lot of slides necessarily for all of these. A couple of topics only have a few slides, but definitely a lot of material right about in the middle. So quick little history. Everybody calls IPv6 the new Internet Protocol, and actually it's not new. It has actually been in an operational state since the very late 90s, and it kick-started over 20 years ago when the IETF engineers kind of said, you know what, those 4.3 billion IPv4 address space will probably run out in the 2000s. And early 2000s, early mid-2000s. And if you kind of understand where things were at that time, this was back in the day when everything was a public v4 address, everything was manually implemented, there was no DHCP, there was no NAT, there was none of the protocol operational aspects of v4 that we know and love today, and just almost wouldn't work without. So that's kind of a little bit of the history, is that the idea was to come up with a new protocol that would have a larger address space and that would actually have a lot of auto configuration, auto magicness to it. And so you can kind of see here in the timelines as they were working on the IP next generation protocol, which is what they were calling it initially, IPNG, the capabilities of IPv4 got extended greatly with technologies like NAT, with technologies like DHCP for automatic addressing, technologies like the private addresses along with NAT. So literally by the time we hit our middle late 90s, all of the concerns about running out of IPv4 addresses were kind of gone. They had switched from the classic Class A, Class B, Class C address blocks to the CIDR notation, so that you could take different address blocks and break them into smaller chunks, and that's how they kept expanding the public address space usage. And then everybody started implementing the private or RFC 1918 IPv4 addresses internally, and they didn't need all the public numbers anymore. So a lot of people started turning back in their large blocks. So all of this stuff was happening, and at the same time they were building some of this auto capability into the new protocol. So often people will say today, well, I got to have NAT. No, NAT was never supposed to be a permanent thing. That was a temporary thing. Private addressing, along with the NAT, again, was kind of a stopgap measure to help expand or extend the capability of the public address space. So maybe understanding some of that, you might see in some of the IPv6 operations as to why they did what they did at the time, and actually some of it you kind of might think now of, why in the world are we still doing that? That seemed archaic, and it could be in some modes. The coolest thing about the V4 to V6 configuration or capability is approximately 4.3 billion IPv4 address completely, and the IPv6 address space is just an unfathomable number. It sounds like a made-up thing, 340 undecillion. And then when you say, well, it's 340 trillion, 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 again, it is a number that is, you got to look it up to actually see that it is a real name. It's big, it's huge. In the foreseeable next couple of generations, we should never run out of v6 addressing, and that's really the biggest bang for the buck from that perspective. Now, there's a lot of other things that go with that. There are still some reserve blocks, there's still some this, there's still some that. But one of the kind of key things, I don't have a chart for it, but of this total capable address block, IANA, who manages all of the IP numbers, IPv4, v6, AS numbers, all those kind of internet numbering conventions, have only allocated, and it's not even that they're anywhere close to being used, but they've only allocated like 3% of this total 340 undecillion. So even if we run out in the next 5 or 6 years, 5, 10 years of the current allocation, they get to go back and put out another small percentage and have huge address space available. So what does the v6 address kind of architecture break down to? 128-bit versus 132, we get that. It's hexadecimal numbering as opposed to just pure decimal, which for a lot of folks will be new. For some of us old guys, we were doing this back in the Novell IPX protocol days, the Apple Talk protocol days. We were making names out of our network addressing. And so as I kind of say, we're back. We can do it again. You've got colons and or double colons that break up the numbering components within a v6 address, as opposed to the dot or the period that our family uses, right? The geeks, we know it as a dot. So trying to break up this total 128-bit number, the 32-bit world, we're used to an octet, a dotted decimal number. In the v6 world, you break up every 16 bits with a colon, and then there's 8 groupings of those 16 bits. Now, the jury's still out as to what you call those components between the colons. There's actually an RFC where they're still kicking around the idea. The most favorite ones are listed there. They're quads, quartets, chunks, hextet. Hexadectet is considered the most numerically correct, but that's a very hard word to say. And if you're from Texas or part of the U.S. South like I am, you have to add a couple of extra syllables in there just because that's what we do with words. Hextet has more recently become a more common use. I've kind of used quads, quartets, and hextets. I don't like chunks. I don't think it's techy enough, but there you have it. That's considered one of the addresses. Now, one of the early components of understanding about IPv6 is, yes, you've got this huge number, but there is a defaulted operation for the use in the, I would call it the breakdown or the assigning of an IP address block. And fundamentally, you just literally divide it in half. So the first 64 bits are for the network, and the second 64 bits are for what's officially known as interface ID, or the IID. Most of us would call it the host ID, or the host address, or the host number. And then you've got your slash and your number, and in this case, the slash 64, it means it's a 64-bit network space. So it's similar to use like in CIDR notation for v4. It's the slash bits, or the slash number, is how many network bits. If you, in playing with v6 and implementing and designing and all those good things around it, stick to this as a guideline, your life will work and your addressing schemes will be good, and you won't have to change anything from the default standard. Now, the network ID is broken up into portions of the IANA allocation to the regional internet registries like an ARIN or a RIPE, and then down to the either ISP or the entity companies that want to get their addresses. And then you typically get to play with somewhere between the last 48 to maybe upwards of 32. Last 32 to 48 bits are kind of your networking space. The most interesting thing about this is as a default usage of the IPv6 addressing, 64-bit network, 64-bit interface ID, that would be a VLAN in our kind of normal thinking. This might be like a /24 in your 10 dot addressing of how you assign a VLAN, let's just say. And a single network for a v4 network space yields, as I show there, 18 billion possible addresses. So your 1/64 is bigger than the entire internet of IPv4 addresses by a factor of 4. It's just huge. Now, when you start looking at the addresses, you're going to end up sometimes with a fair amount of zeros here and there, and it just depends on how you do your allocations, especially if you're doing like DHCP and things like that. But we have some shorthand that we can use. If you look through the middle of this, you can basically see a fully extended out IPv6 address, and you've got at the second and third hextats all zeros. The fourth hextat's got a leading 0, and then the fifth, sixth, and seventh hextats are all zeros. So one of our shorthand things is to be able to drop all leading zeros. So like that 0A52 can be shortened to simply A52. And then you can drop groupings of zeros to what's called a double colon. But you can only do that one time within an address. So you can use the double colon compression like in the option 1 where we took out the 2 groupings of zeros, or you can take it out in that option 2 with that 3 grouping. And then whatever's left, you still have to have a value, like say option 1 has got the 2001 : A52 : you still have to have a 0. You still have to have a number in that space because we can't drop that 4th or 5th, 6th, and 7th hextats of zeros. So you have to at least drop the first 3. So that is the dropping leading zeros. And then you've got a similar operation in option 2. So fundamentally, if you're ever presented in an IPv6 test or a test that has v6 questions in it, any one of these 3 representations is an accurate and correct. If you're going to use the shorthand, which is considered the best practice, then it's the best practice of the where do you do it is whatever yields the smallest number, or the most dropping of zeros, as it were. So the option 2 in this example would be the considered better practice of use of the double colon process. So here's the example where, oh, go ahead.
I'm going to train wreck you right there. Sorry about that. We did have a question come up. Graham Michael asks, is it also possible to put a single 0 in each octet? But I think you were getting to that with the option 2.
A single 0. Yes. Yeah, either one of those options basically indicates that. I'm not sure if I answered that question correctly, though.
So I guess what he's getting at is where you have the double colon in the sets of consecutive zeros. So in the fully expanded thing, the blue, green, blue, would it be possible to put a single 0 in each one of those blue, green, blue spots?
Yes, that's the option 1.
Okay. Just wanted to be absolutely clear. Did we get that cleared up for you, Mr. Graham? As he's typing feverishly. No, option 1. Okay, option 1 has a double colon in the first block. So,
right.
So I guess he's asking if can you do it where you don't have any double colons? You can just put single zeros in anywhere.
Oh yeah, yes. You could say 2001 : 0 : 0 : A52 : 0 : 0 : 0 : 3D16. You could do that, and that is an acceptable usage, and it would be an acceptable view. It would not be considered the best use of the shorthand notation, but that's not an illegal use. Hopefully that makes sense. From a test question perspective, it's still a valid address representation.
Outstanding. All right, well, I think that cleared that up. I'm going to go ahead and mute. Thank you.
Awesome. I just want to show real quickly that if you were to take that number and put in 2 sets of double colons, what you don't know is how many bits are represented by each set of double colons. Is it a single group of 4? Is it a double? Is it a triple the first time? And the same thing for the second time. So that's why not only should you not do this, I have yet to find any kind of operating system that even allows me to. So from a test question perspective, this is that number with the 2001:A52:3D16 is not a correct representation of an IPv6 address. So just about any of those others would certainly work out. Now, the early parts of the v6 concept, or IPNG, was this auto address capability. And how do you get the network address down to a client or to a host or to a node, what they actually call it? And then how does the node self-assign its interface ID? So in the early days, they said, well, every network interface has a MAC address. And that's a 48-bit address. I've got to shoehorn that into a 64-bit space. Well, there was already an existing IEEE standard called the UE64, and that said to basically split that 48-bit address in half between the company ID and the OID and the manufacturer individual interface number, and put in some padding, the FFFE, and that now made you capable with a 64-bit address. The IPv6 team wanted to know that this was done very specifically to be used as an IPv6 interface ID, so they added a second process that said take the 7th bit of the first byte, known as the local and global bit, and invert it. And that way, that kind of gave it a little bit more of a unique status, not just a quote UE64 number, but a modified UE64 number used for an IPv6 interface ID. Well, that was all fine and good. And then a lot of people say, well, what about with that MAC address? You could very easily extrapolate what kind of device that is. So there was a process led by Microsoft to come up with what's known now as these privacy extensions, which basically said just use a random number generator process to create a 64-bit number. And then they added another component to it, said that not only create one, but create two, and we'll call one of them a temporary. And the temporary address will change on some periodic basis. The RFCs don't state how frequent that temporary should change, but it should. And then that temporary address is actually the v6 address that's used for communications. Because it does change on some periodic basis, it would be harder for somebody to find that same address at that same device every time. So we had the MAC address, which was a very static process. You had this random number generator, and there was actually a third process that was part of the initial standard from a security aspect, and that you would use IPsec. And that was one of the things that v6 was also being designed with initially, was to be a more secure protocol. IPsec would be built in. Everything would be secure and encrypted. And so they came up with this process of using a regular cryptography algorithm to do it. Of course, the downside became is how do you get the keys to a client that's not trusted on the network yet so that you can trust the IP address that you give it? So therefore, this cryptography method, or SYND process, Secure Neighbor Discovery is what SYND stands for, never came to fruition and was actually deprecated from a you must do it to you can do it if you want. And literally as soon as that happened, most manufacturers quit doing any support for it. Microsoft doesn't support it even yet. There's not any clients for the Mac for it. There are some third-party open source clients for Linux and Mac and Windows, but they're just that. They're not by the manufacturers. So you've got those three different methods possible to get an interface ID, or again, what we would normally think of as the host ID. Now, a quick look at the different kinds of addresses. We are relatively the same, except for one key difference is in a v6 world, there is no broadcast type traffic. Everything is either fundamentally a unicast or a multicast. Everything that we did with broadcast traffic in a v4 world is now multicast, not multicast. I misspelled that. Sorry, folks. I should say multicast. And then you have either what will be called on-link multicast, which is the replacement for broadcast traffic, and then you have routed multicast traffic, which we would have in a normal v4 world as well. So that's a key difference. There's no broadcast traffic in a v6 world, just period. It just doesn't exist. It's all local on the network, or it goes to off the network multicast or even local network multicast. So a quick look at the kinds of scopes. One of the things that you'll see much, much different in a v6 world once I get my kind of demos going here is that there are lots of different addresses on a v6 interface. In a v4 world, you have one v4 address per network on an interface. So on a regular, in-station client, it would have one v4 address. It could either be the PIPA address, the 169.254/16. It could be, I'll call it a public address, or it could be an RFC 1918 address. But you can only have one. You can have them in different networks, but only one address per any particular network. In a v6 world, you will have what's called the link local. It's an auto-assigned. You will have, if you're doing any kind of off-net traffic, a global unicast. And there is an assignment for what's called unique local, which would be likened to the RFC 1918. But since there is no official NAT technology in v6, if you use that unique local, you can never get off of that local network or local enterprise even and route to the outside world with it. There's no NAT like we think of today. So you might actually have a combination of all three of these types of IPv6 scoped addresses. So some of this we'll start to see as we play a little bit more here. In the special address, it's just a real quick slide to kind of show how your default route statements would look like in your router, routing functions, a little bit about the loopback address. It's a little bit easier. It's :1/128. The link local I referred to, the 169.254 again being the IPv4 of PIPA. And in an IPv6 world, it's known as an FE80 : address. And then you can see this global unicast, the unique locals, which are similar to private RFC 1918 and v4, and then there even the official documentation or example type address reserved areas in both our protocols here. Now, again, still trying to set the base here. In a v6 environment, we have two kinds of timers as far as how the address can be used. In a v4 world, there's a single timer, and the only place you really ever see that timer is typically from a DHCP server. A scope is configuring an address block. It's going to hand out numbers from a pool. It's going to give out the default gateway. It's going to give out the network mask, and there's usually a timer involved of how long that address is good for. In the v6 world, we have two kinds of timers. One known as the preferred timer, which is a new one, and the other the valid timer, which is pretty much like we think of in a v4 world. And the reason for these timers was to be able to change your addressing, your network prefixes on the fly while everything is still running without having to take down a network to do a readdressing. And anybody who's ever readdressed a network knows that it works so well, right? You send out your email Friday afternoon, you tell everybody to turn their computers off, you're going to do some work on the network over the weekend. Everybody comes in on the network team, they change all the stuff, we come in Monday morning, and there are still things that don't work. There's the secret squirrel rooms that have devices that we didn't know about. Somebody didn't get the email, didn't shut their computers down, and the next thing you know, you still spend another day or two getting it cleaned up. With this dual lifetime world in a v6, this preferred lifetime is the time that you can actually send and receive new and existing communications. When the preferred lifetimer times out, then the address goes into what's known as a deprecated state. It's still a valid address to be used in time, but only to finish up existing communications. Any new communications have to start with a new address. And depending on how the address is assigned, whether it's automatic through DHCP, whether it's automatic through a couple of other processes we're going to talk about, it may still be the same address. You can interject new network spaces, and the IPv6 hosts will get this new address. When their old address exits its preferred lifetime, they'll start using this new address, finish up their old business, and then now they're using their new address, and their old address will basically just go away. It'll disappear once it completely deprecates out and times out. So you can literally readdress an entire network environment if it's following all of the IPv6 address auto configuration functions, and never have to go touch devices. People don't have to turn them off. And that's where this dual timer environment comes from. So even in a DHCP v6 server, there are now 2 timer values that you can set. And typically the preferred is about 75% of the time of a valid lifetime.
Hey Jeff, looks like we have a question.
Okay.
Can you set the timers from DHCP v6 server?
Yes. Yes, you
Sorry,
can.
delayed.
No worries. You say I'm moving kind of fast, so it's all right. Just a quick note on the header for folks to kind of see. The part of the whole thing, again, about v6 is they were starting over from scratch, and so part of it was to kind of clean it up. So you can see there's a lot of fields that they didn't keep. They changed some of the operation. We've got traffic class, which is similar to the type of service. We also have a flow label, which is new, and it's targeted to be used like into a QoS servicing with a lot more capability. It's just not being used at this time. So we've got this big chunk of address space that's literally not used at the moment. But that's the basic layout of a v4 to v6 header. So again, quite a few of the same things. We've got this next header thing that I'm going to spend just another couple of minutes on because it gave us a lot of functionality to do what they call these extension headers, so that you can almost send out multiple functions within a single packet to, quote, do this, then do this, then do this. And some predefined functions of the extension headers. It's not actually a technology that's really being used much yet, but it's there. There's also quite a bit of conversations been going on the last few months about the security aspect and the security vulnerability about this whole thing with extension headers. So you can actually go out and do a search in your favorite search engine and find a little bit of noise about the IPv6 header extensions. So some of those things might be, you can change some hop to hop. You can, if it's a routing header, you can change some information. There's just a number of components within that extension header, and previously we didn't really have the same kind of function in a v4 world. You would, do a function, do another function, do another function, but now we can kind of chain them together inside of a packet. Here's a little bit of a picture of what that looks like coming up. You've got your header, then you can have the next header which says, okay, now do this, and again, you can just kind of keep chaining these things across, but not really used, certainly not at the client level and not much at the, I would call it, quote, router level at this stage of the game. Now, one of the key things about IPv6, just like IPv4, you've got ICMP. Now everything is for v6 under ICMP v6. And then we have this whole new topic called neighbor discovery. So this kind of boils that down to a little bit. The IPv6 neighbor discovery protocol suite pretty much encompasses all one thing, where previously we had ARPs and different functions with ARPs and different router packets and a couple other things. They're all kind of more cohesively designed under ICMP v6 under this neighbor discovery protocol section. So I'm going to kind of break through these a little bit. Pretty much everything that you know about ICMP has a counterpart to v6. There's going to be some new ones. There are still a breakdown. We can still do things with ping. You still have all the same kind of things you did before. I'm going to talk a little bit about this path MTU information just in a minute, and then a little bit of a breakdown of the message categories here. So really, for everything you know about v4, there's going to be a v6 counterpart and then some. Or there'll be, like in the case there's no broadcast, but there's a multicast on-link type traffic that you would think of like broadcast. So one of the key things is, from a security aspect, a lot of folks will say, well, let's just turn off ICMP v6 and that'll take care of it. And if you turn off or block ICMP v6 traffic at, at firewall borders or routing borders, inside of the network, v6 just basically won't work. We have to have a lot of ICMPv6 type messages available. Now you can go in and kind of hunt and peck and turn off some or only allow some and deny all the rest, but you've got to be really, really careful about the ones that you take like that. Now, one of the key things that's different in a v6 world compared to the v4 is how MTU is used and where packets can get broken up. In the case of the v4 world, the routers set the MTU size, and if a packet comes in too big, then the router function will fragment the packet and send them out in the smaller chunks. In a v6 world, the router doesn't do that anymore. You can set MTU sizes at routers, you can actually set MTU sizes at clients, at any place. But if a router has an MTU size that's smaller than the packet coming in, the router actually sends a message back to the client. It effectively says, too big, try it again smaller. And this now takes some of that overhead work off of routers. So my little diagram here shows us going from node A to node B through multiple router hops. And when it hits router C, the router B to C link, at router C, it has a smaller MTU definition. So when the packet hits, a 1500 byte packet hits router C's interface, it goes, no, I can't do that. And it will actually send this ICMPv6 packet too big message back to node A, and it's up to node A, who now knows that size number because it's built into that message, to resubmit its transmission at 1300 byte size packets and not 1500 bytes. So it's almost the exact opposite use of PathMTU compared to the v4 world. I don't really find a lot of places changing the maximum size, but you certainly could, for whatever reason, along a path or a slower link path or something like that. So that was one of the very specific differences I kind of wanted to point out between ICMP and ICMPv6. Now this neighbor discovery protocol, it's interesting because we have neighbor discovery protocol suite and then very specific components that are also called neighbor discovery. And it gets a little tricky sometimes, but under this neighbor discovery protocol is how you find out about other devices, how you communicate at the root level, kind of like the old, I got an ARP for my router, I've got an ARP for my neighbor functionality, and those are now all put into this neighbor discovery protocol function. So these are the four key ones from a v6 operational standpoint. Devices will send out messages called router solicitations looking for an IPv6 router on their network or on their link. Routers will send out advertisements back. Neighbor solicitations are kind of like the I'm ARPing from my neighbor, and then the neighbor advertisements the reply. So since I've just said those, I'm going to break these down just a little bit. The neighbor solicitation is used to find your neighbor. It's also the process of what you do is what's called duplicate address detection to make sure that there's nobody out there with your same address. It's kind of like the initial stages of a v4 interface where it effectively ARPs for itself. Now we do a test to see if anybody has my same number. They also use it if I've been communicating to a device and I haven't lately. I can use this neighbor unreachability detection, which is kind of like a, hello, are you still out there? I've talked to you before, are you still there? And then a little bit of formatting of the packet, and people can come back and look at that later on as well. The neighbor advertisement's easy. It's a reply to a neighbor solicitation. Somebody's looking for me. If I'm that, I send a neighbor advertisement back to them. It's just that simple. Now, this router solicitation message is new. We don't really have a normally used counterpart like this in v4. In a v6 world, and this is really, really important for people to understand, this is probably the key thing to make your v6 world work correctly, is that clients find out about their router or their default gateway via this router solicitation message, not from a DHCP server, not from statically configuring it. It finds it out because it sends out this message, this router solicitation, looking for a router advertisement reply. And there are multiple uses of this router advertisement, but the one of the key components is it tells the client that I'm your gateway. And that's how this world works. And I'll say this multiple times, we'll see this multiple times. Now, this router advertisement can do other things. It can provide a client the network prefix. This is how all this automagic stuff came about in this world. And the routers would tell the clients their address or their network prefix. The clients could self-derive their interface ID, and you have a network going, and you didn't have to have servers. Remember, this whole thing started before we even had DHCP in a regular networking world. We had BootP, but BootP wasn't really used down in at a client level yet. That's kind of where DHCP comes out. So you see some of the things here. You're going to see this more as we come up and through it. This last little bit in talking about the neighbor discovery protocol is this duplicate address detection. No matter what kind of v6 address a node or an interface tries to use, whether it's a link local, a global unicast, a unique local address, whatever, every single address must perform the DAD, the duplicate address detection test, and verify it's unique and then continue on. Now, there's been some added capabilities so you don't have to wait as long. They call it deterministic DAD, which says go ahead and start using your new address as soon as you get it, but you've got to do the DAD test also. So their processes are done in parallel, and it literally saves about 2 to 3 seconds in the v6 address coming up by not having to wait for the DAD to occur before the address can be used. So that's why they kind of added that extra little bit to it. Now you have an ARP cache in a v4 world. We have a neighbor cache in a v6 world. Same concept. I need to keep a cache of the different devices I've talked to, whether it's my default gateways or my other friends, my other neighbors on the network. The same concept, and you have another table, another cache table. And we have a couple of different states in here. As you can see, reachable means we've been talking, and the timer hasn't timed out, which means we've continued to talk. And then you've got the different states of stale, I haven't talked in a while. We're trying to find out if they're still there. The very initial time is the incomplete. We're trying to do an address solution, but we haven't quite got there yet. So there's a couple of different things that relate in the neighbor cache. Not really a big surprise here, just some of the namings. Okay, moving along here. I've got a lot less time than I expected because I've talked too much, but I wanted to show you this. This is a magic slide. Everything that you want to know about IPv6 address auto configuration is basically here. You have to have certain router bits set, or they call them flags, within that router advertisement in order to achieve a certain kind of addressing function. This is completely different than what we have in v4. And depending on which address automatic or auto configuration address function you want to use depends on what it yields as far as how many addresses, how do you get your DNS and your domain and your download servers and your time servers, all that information, whether or not you want to use DHCP v6 or not, or you want to use some combination. Everything's on this slide. This is a culmination of like 3 different RFCs about this whole environment that tends to help out a little bit. So we're going to start off with this link local. This is just basically an interface, an operating system with an IPv6 stack. As soon as it's enabled, which it is in most modern most modern operating systems these days, you'll get this link local. So if you've ever done an IP config or an IF config and you've seen an FE80 : something address, that's known as the v6 link local. You must have one. You cannot turn that off. If you turn it off, v6 doesn't work or won't work correctly. Because your link local address is used to talk to your router, if you have one. Now the thing about link local, you don't... Yep, go ahead.
Are these link local addresses globally routable?
No, they are not.
Okay.
They are link on link In fact, you could have, what's really hard to understand sometimes, is say a router with multiple interfaces. Each interface could have the same link local, and that's very common to do. And it's okay to do because they're only good for that layer 2 domain, that VLAN level. So yeah, it's not a routable address, and I've not found it that I could make it routable in any router software. No, it doesn't. I haven't tested everything in the world, but I've tested quite a few different platforms. So you don't need servers, you don't need routers, you don't need anything. So again, this is similar to the v4 APIP address. When Microsoft came up with that 169.254 back in the Windows XP days, where devices could sit there and communicate, on a local network segment. They can't route off, they can't do anything else, but they could at least share data. You could ghost image a bunch of computers, so you can do the same thing with the link local address in a v6 world. So you can actually start playing with v6 with a couple of devices, on a back-to-back Ethernet cable and crossover cable, and actually play and not have to spend any serious money, as it were. Now, the more interesting thing about using this link local is that because the whole concept of the link local could be the same link local on multiple interfaces in any given device, whether it's a Windows computer or a Cisco router or multiple interface firewall, any of those things. If you want to use that link local interface to talk to other link local devices, you have to actually specify the interface you want to use. Most easiest examination of that would be like using a source interface. Sometimes on routers we do, or firewalls we do that kind of things. So this is just something you have to know. You don't normally really use a lot of your link local addressing, but it's just kind of an example. I've got a few slides here to show. Here's a Windows 7 computer, and you can kind of see in red that it's link local address. It happens to be on interface 12. So if I wanted to ping another device on my network, I would have to say I want to ping that other device's link local address, and then give it its interface number. In this case, %12 is the way Microsoft looks at it. In a Mac world, in this case, it's on interface EN0. And so if I wanted to do a ping, you can kind of see up here at the top, you do the ping, say I want to go out EN0, and that way the operating system knows exactly what interface. Now, most of our client-type operating systems don't have the same link local address on every interface. If you've got multiple Ethernets or Ethernet and wireless, all of their link locals are typically unique. But you still have to do this process. Now, it's really interesting, though, is the Microsoft in Windows 7 and 8 are a little bit more intelligent. They actually sometimes know which interface to go out, so you don't always even have to put that interface number. But it's rather interesting. A Cisco switch, in this case, has got a link local address of FE80::5. And so up here, if I want to ping another IPv6 address, it comes up and says, what output interface do you want to use? I typed in VLAN2, and then it pings. If you don't put the output interface, then you just get an error message. Another switch vendor, HP's layer 3 switch here, same kind of thing, FE80::9 down here in red at the bottom of that screen. And when I go to ping out, I say ping to that device %VLAN2. So it's literally you have to find the particular syntax for every operating system. So the link local, again, is on link only, can't be routed, can't do anything else with it, you can't get to it. Life is good. Now it's time to get we'll call it a global unicast address or a routable address. And our first type of operation is known as SLAC, or stateless address auto configuration. And SLAC requires now a router, and it requires a couple of flags to be enabled. We call them the A flag and the L flag. The A flag means auto configuration, and L flag means on-link router. The downside for a SLAC-only world is that there is no specific functions to get DNS, domain name, etc. So Slack is only partially useful in a real-world deployment. You'd have to manually configure or push out on some sort of login process the other information. There's actually been some changes in the RFCs that the router advertisement could have a domain name and a DNS, but none of the client operating systems are using those fields yet. So even if the router advertisement has it, nobody can use it. So Slack only is not really that practically useful in a real world scenario, in a apples to apples type comparison of use. So here's a bit about Slack. Router advertisement gives you your network prefix. You self-derive your interface ID using one of those 3 methods we talked about earlier. And the basic process is a client would come online, send out this router solicitation message. Any routers out there, routers respond. They have these flags on. The clients do their bit. They do the DAD. If everything's unique, ta-da, you've got an address. But you got to do everything with addressing. You don't have any DNS information that way. So again, Slack by itself. Here's a quick view of a packet showing the flags. The flags we're looking for down in the lower red outline box with the L flag on and the A flag on here. These other 2 flags I'll talk about here in just a minute coming up. And that is known as stateful or DHCP-v6 use. Now, we're used to most of our operating systems just coming up and having DHCP enabled, and they basically send out a discovery packet, and they're looking for a DHCP server to reply, whether it's on the network or there's an IP helper address, a DHCP relay. In a v6 world, it doesn't really operate that way yet, kinda. It's supposed to operate where the client will come online and look for these flags to be set and then ask for a DHCP v6 server. And that's mostly the way it works, but there are a couple of operating systems, Windows for one, that may do it even without the proper being told to do it. And that's the key here. The router advertisement is telling the client that, no, I'm not giving you your address, network prefix. You go ask for a DHCP v6 server to give you everything. And that's kind of it. That's pretty much the way it works. Client will come online. I'm going to go straight over to that slide here. Client will come online, interprets the router advertisement. It says ask a DHCP v6 server. The client sends out now a different kind of message. It's known as a solicit message. The server responds with an advertise, here I am. The client sends back a request to give me stuff, and the server says, here's your stuff. The client does its DAD test and then comes online. And now this is pretty much what we're used to in a v4 world from an operations kind of viewpoint. Here's again a little bit about the router advertisement, the M flag, and the L flag. Now, one of the key things is if you read most router documentation, they tell you, oh, you want DHCP v6 support, go turn on the M flag. What they failed to tell you was that you had to turn off the A flag, and then you end up with more addresses than you wanted. And I'm going to talk about that here in just a minute. I mentioned this a while ago about DHCP and DHCP v6. The key difference is the default gateway is not learned by a v6 client through DHCP v6. In fact, according to the RFC, there is not even a place in a DHCP v6 field, and no DHCP v6 routers really support this yet, to put a default gateway in, because the client's supposed to learn it from the router advertisement. They're talking about, there's a draft RFC in place. We're talking about trying to change this behavior, but again, even if they change it at a standard level, it still means we have to wait for everybody else to catch up. They haven't caught up on the other thing. I'm not sure if they'd catch up to this. And really, it's people looking for parity. They're just used to doing it a certain way. We've been doing it for 15, 16, 17, 18, 19 years the same way now. We just kind of want parity. But previously, this was kind of in that in-between state where it was all new technology. There's a combination of saying we want the router to control the network prefix, but we want the client to still get DHCP or DNS and domain name info, so they call it stateless DHCP v6. It's half Slack, half DHCP v6, or half stateful. And this is, I would say, not as popular as DHCP v6 type operations, but it's getting close, where we have more network control as opposed to all at the server level. So a little bit about that. Again, it's part Slack, where the router advertisement gives the client the prefix, and then the client asks the DHCP server for basically other information. And there's a different flag to get set. So the same similar process.
Hold up.
Yep.
We did have a quick question come up. I think you may, like as I'm looking over the slide, you may be getting to it anyways. The question was, DHCP v6 is done on a layer 2 domain or per layer 2 domain, so each layer 2 can have different Slack or DHCP v6 options? That's
correct.
Is that okay? Awesome. Thank you.
You bet. So the stateless DHCP process, still, router advertisement, certain flags are set, and the client acts accordingly. In this case, it's going to do multiple things. Self-drive is on addressing, but asks the DHCP server for everything else. And again, the flags. All this is controlled by flags, and yes, at the layer 2 domain level, you can set the router advertisements with different flags. You can even tweak some of the client operating systems. You could have, quote-unquote, all the flags on, and then even tell some clients to pick up specific flags. Some clients do not listen to the A flag. Some clients do not listen to the M flag. I personally don't recommend that, but it is certainly possible to do it that way. In my mind, it would be better to break everything up so that the router advertisement and all clients on that network operate the same way. Now, this last one kind of talks about that. Is like if all the flags are on, if you look to the bottom far right column row there, the problem with this all flags on and not touching the clients in any other way is that you get too many addresses. And then generally what happens is the address you think you're wanting to be working on is not the address that you're going to be working on. So I basically call this an undesired configuration. And it's typically because literally reading some of the router manufacturer's documentation and just turning on the flags they say to turn on and not turning off others. And it's an accident. And it's just because it's not always documented well. That's kind of where I came up with those charts. So you could control the clients to listen to certain flags or not, but I don't think that that's a safe behavior from a perspective of control. All right, so the last little bit is that, of course, you could do a manual address. I put it in this as a chart just to show it's not auto configuration, of course, but the key is you still have to have a router advertisement to still tell the client to use a gateway. Now, in the case of some operating systems, and Windows Vista 7 and 8 are one of those, there is a default gateway field for IPv6 protocol. You really shouldn't fill in that field if you're doing a manual world, because you should have a router on that network that's sending out a router advertisement with only the L flag on, and the client would learn the default gateway. If you choose not to do it that way, you don't break any rules per se, but you take away the capability of making changes from that router advertisements function. But I still put it in here. What's really interesting, though, in the case of a v4 v6 comparison, in v4, when you manually enter address, that a PIPA address and or the DHCP process for the client stopped, and it only uses that manual address. And that's not necessarily the case with all operating systems for v6. In fact, some of the Windows operating systems, you can manually configure an address, but still have a router advertisement with either Slack, stateful, or stateless turned on, those particular flags. And that client will get addresses from that process as well. And generally, it's not the manual address that'll get used then, which trips people up. So it's kind of a, you got to be careful in paying attention to those router advertisements and their configurations. So that's kind of what this next slide is. Go ahead.
Okay, you may have touched on it, but how do router advertisements work with VRRP?
With VRRP? Well,
VRRP, yes.
The best part about that is you still set up your VRP v3, I think they call it, for IPv6 with the virtual IP. And the router advertisement still sends that out as the address that, I'm your default gateway. And in the case of, a pair or more VRP routers, there's only one responding at the moment to that address. If the primary or that master goes down, the backup or the secondary comes online, they still answer to the same address. So that kind of falls in line with this whole operation of don't statically configure v6 gateways. Let the routers take care of it, take care of their job. And then it doesn't matter whether it's VRP. There's actually another concept in IPv6 called, I just lost it, that basically does router redirects. And it was kind of a precursor to HSRP or VRP type technology where two routers on a network, your client knows about both of them because they both send out router advertisements. You send your information to your first default gateway and it says, well, actually, where you want to go, it's closer to router number 2. So send all your packets to router number 2 from now on. And again, that's kind of all part of the underlying v6 operation. So for VRP, there's really no change in how we do it because it's still all controlled at the routers.
Okay, we did have one other question.
Looks like we have
Twitter. Oh, you got that one? Okay.
Do you see much unique local alongside global inside small orgs to avoid renumbering at ISP change?
Oh, I can't say that I myself have. I don't hear a lot of talk about it because most of the v6 technologists are basically saying, don't do that. Don't use the unique local, trying to keep your stuff local, because you still can't really get off net with that unique local. Most people say, but that's my protection, that's my security. And it's like, no, your security is at your router and your firewall. There's really no reason to have to do that. The general best use of the unique local is to just use it for like a self-contained lab or a self-contained network that never gets out to the outside world and needs to be protected even inside. Because even if your provider, you change providers and now you have to do a readdress, you don't have to touch all the devices unless everything is statically configured. Now then you do, but that happens no matter what. And all this auto configuration capability really does work well for clients, especially with these timers, because you can adjust the frequency of these router advertisements that go out. You can adjust the timers of the preferred and valid lifetimes for the client. And you can send out router advertisements every 10 seconds. And then all the clients will get all this new information, and you could readdress very, very quickly. And you can do it on the fly. So even for the smaller environments that might change, it's in my mind not near as hard as it's been in a v4 world. Because every time in a v4 world, we typically have to change not only our public facing, but some of our private to public stuff, our virtual IPs. We end up having to change a lot of stuff from that perspective. Maybe not so much internally, but it's not as hard a process in a v6 world. So a lot of people are trying to say just don't even go there. You don't need to. Just be, all you have to be is equally as good at your control of what comes in and out of your network. So not a great answer, but my best reply. Do we have others? Can you guys still hear me?
Not at the moment.
Okay. All right. So I'm going to blast through some of this pretty quick. It's getting more and more easy to say that just about all operating systems support v6 in one way or another. In the switch router world, and it depends on brand, it depends on family, it depends on age. Most everything within the last 5 or 6 years probably support IPv6. For routing, even then, most routing functionality for v6 is supported. It's just typically not an enabled protocol by default. And you typically just have to either turn it on, you may have to bump up with a feature in a particular bit of software. The most critical thing really at routers, and whether it's layer 3 switches or classic routers, is that the older the product, the bigger the chance that the v6 routing function is now done in software or at the processor level and not done in the ASICs at the hardware. More of the newer technology, now v6 is in ASICs, and it's maybe not quite such an issue from a performance viewpoint, but it's still just something to kind of understand a little bit about. But it's pretty much there. You just got to either obtain the feature or turn it on. If we take a quick look at some of the server operating systems, just very quick, Microsoft introduced the v6 protocol at Server 2003. The only thing is it was an add-on, it was all CLI, and none of the server services use it. So it's one of those, it was a proof of concept and nothing more. And it was not recommended to try to be used in a real, full-blown server environment because, again, the applications just didn't support it. From Windows 2008 server and above, it's a their protocol. It's an enabled by default protocol. You can configure it at the command line in the GUI. All the operating system applications work with it, and it's just kind of like done. We don't even ask that question anymore. So even a couple of years ago, it was one of those maybe a way to start moving out of Windows 2003 server, and Microsoft is doing other things that kind of help that process along as well. So we have that. Linux has supported v6 probably the longest of all the operating system, whether you call it server or client, kind of didn't matter. Typically an enabled protocol, and that's the key. When I do presentations, like face-to-face presentations about v6, I typically ask everybody, who's running v6, and a lot of people say, "Oh, I'm not." And it's like, yeah, but if you've got any modern operating system, you probably are, especially at the client level. Microsoft again introduced it at Windows XP, very limited, no DHCP v6 support. It was a proof of concept. We can make our operating system speak v6 at a basic level. With Vista and above, it's an enabled protocol. It's fully functional, fully capable, and again, it's an on. And a lot of people thought they could turn off IPv6 by deselecting the protocol box on an interface, and that didn't really do it. Microsoft came out with a couple of other options like registry entries to turn it off. And then about 3 years ago, they backtracked on that because they started coming out with applications that required v6, like direct access, like Exchange 10. They require v6 in the background. So Microsoft does not recommend trying to turn off v6 any longer, and virtually nobody does. And that's kind of the state we're in, is that some network level applications are starting to prefer v6. The operating systems basically should prefer IPv6 if it's on and quote unquote running. And since it's on, it should be there. Should be the primary operating protocol. And I put in this kind of bucket of peripherals as everything else, and this is where the support is much, much more sporadic, and it's typically because of embedded systems, small footprint processor, memory capability systems. Most voice over IP phones of probably now about 6 years or so ago old won't support v6 at all. They probably can't be flashed or anything. All of our other smaller world, barcode readers, scanners, environmental control systems, all that kind of stuff, it's going to take a little bit longer. But even looking at things like the Raspberry Pi card, a little computer board for embedded systems usage and things like that, it supports a full v6 stack. So it's a lot of fun playing with that. We can even make routers out of Raspberry Pi. It's just a blast. Now there is a process, because you might have multiple addresses in a v6 world, and v6 is considered the preferred protocol. There's a little bit of an address selection process. There was an old way, there's a newer way, and not all the operating systems really do it the same. Not everybody's up to speed. There was another set of processes called the Happy Eyeballs RFC that basically said, okay, This was when V6 was starting to appear places, and people were trying to go to, let's just say, websites. Sometimes they could go V6, sometimes they could go V4, depending on the host. Sometimes some of the host would be V6, but some of its data content would be coming from V4 machines, and so there was delays. And this whole idea of happy eyeballs is basically to say, if I can get their V6, use it. If I can't, use V4. But always ask the questions in parallel and use whichever one you get an answer for first. In the case of like the most latest use of the which address in order, there's a destination and a source selection process. You just follow a basic set of things. Which address, is the best? It's the most favored. It's the closest, all the way down to, nothing else matches but my last one. And so we're still in a little bit of an interesting state as more and more systems on the public internet go to V6. It's getting easier and easier for V6 enabled clients with V6 addressing to actually get out to them. But like everything else, there's processes to follow, rules to follow. Routing is a quick one. For every V4 routing protocol we're pretty much familiar with, there is a V6 counterpart. And in often cases, for RIP, OSPF, and the IGRP, they're almost always a separate routing process. For ISIS, it could be, and for BGP, it just may be an updated version. They call it now MP, or multi-protocol BGP. But the easiest way to think about when you start implementing a V6 world alongside a V4 world, and we call this dual stack, is that in your routing device, whether it's a layer 3 switch, a classic router, a firewall doing router, whatever, you will probably have two sets of configuration, one for your V4 world and one for your V6 world. Sometimes they may be under the same process, but generally they may not, or they shouldn't. They might not be. So we have a little bit of that that we have to kind of work for. And most of the router vendors that are supporting V6 now have this. Of course, the IGRP only for Cisco world. ISIS, I found a little bit of lag in some of the router vendors for ISIS for V6 extensions, and similarly for BGP4 going to MP BGP. It's a little bit behind for some router companies, or that routing process or functionality may be in software only for now until they move it into the hardware later. But for the most part, everybody does it. The more interesting bit is that some router companies have their V6 routing as an enabled function as soon as you start adding IPv6 addresses to interfaces. So this is, again, one of those things that has to be looked at. In a V6 world, this is a read the manual first, all right? Read up on all the different systems that you've got and look and see what their default states are, because you will get surprised, and it may be not as pleasant as a surprise as you're thinking. So these are just the ones that I've played with in my lab. One of the other things that I kind of have note there at the bottom is that if you're doing point-to-point links, or you've got devices that don't have quote-unquote clients, I'm not quite sure what those might be, but you've got interfaces like that, then you don't need to have those router advertisements. And so that's a feature that you can typically disable. You still need routing, you just don't need the router advertisement, and again, like the point-to-point links. So we'll talk a little bit about applications. Do I still have enough time, guys?
Really, it kind of depends on you. Like, I'm more than happy to let you go all 5 hours if you need.
No. I'm going to try to keep it to not much more than about 15. Let's see, what are we at? Yeah, hour 15, about another 15 or 20 minutes, and I'll top it. Because I know everybody else has got things to do too. Okay.
Well, it's entirely up to you, and I mean, we can have you come again for a second one as a follow-up as well. So we did have a question. Graham again, how would you handle IPv6 over an IPv4 MPLS circuit? I'm asking it as a question both to you and to Graham to make sure I captured the question right.
There is support for v6 over MPLS. You typically have to run it as a separate process, perhaps. You could do some v6 tunneling through a v4 link that was in an MPLS network as well. So there are a couple of options for that.
Okay. So apparently AT&T look at you funny when you mention IPv6.
Oh, no kidding. yeah, yeah, I have AT&T. Yeah, I don't like AT&T because they're behind. But yeah, they're not quite there. They like to say things, and if there's any AT&T people online, I'm sorry. This is my personal opinion, but they're behind the other guys, they're keeping it a well-guarded secret. I'm not sure which. But yeah, there are a couple ways, and in fact, sometimes the tunneling of it through v4 is how you have to get around, especially providers that don't do it yet. So there are a couple. They're called transition mechanisms / tunnels, and so there are a couple ways to do that.
Okay, awesome. Thank you.
You bet. Pleasure. So keep those questions coming. Good questions.
I was going to say, since we're getting closer to the wrap point, maybe I'll circle you back on this one. There was a... Wow, I deleted the original question. Never mind. I said I was going to loop you back to the QoS and VoIP and so on, and maybe how it handles fragmentation or so. But I'll ask Mr. Graham to retype the question, and then I'll just interrupt you when we get back there.
Okay, great.
It says, how does the QoS change for use with VoIP?
No difference.
Is that the correct question?
There's no difference. You do it the same way. The QoS definitions are the same right now as they are in v4. Again, that flow label will provide more options and more granularity in controls, but it hasn't been programmed or hasn't been used yet. They haven't done anything with it. So QoS is pretty much the same. Fragmentation, again, is now handled at the client or the device level, not at the routers for v6.
Okie dokie.
All right, so some of these network applications, I want to kind of go through these to basically say everything that you do in v4 works in v6 from I call it network application, the things that we use on access and managing back into the network. Here's the DHCP v6 process, just slightly different names, trying to do that comparison to the v4 world. Here's a quick little set of packets where the router gets sent out its advertisement. Within that advertisement were certain bits for DHCP set, so the client did its solicit. The server did its advertise, I'm here. The client said, okay, can I have an address? That's that request message down over here. And then finally the server gets its reply with, here's your address, here's your DNS and your domain name and anything else you asked for that I can give you. So it's not drastically different, just different names. We still have DHCP v6 relay, and what was really interesting, 3 and 4 years ago, about half of the router vendors didn't support DHCP v6 relay, which we typically think of that's a helper address, when actually in v4 there's two things. There is a relay function that's typically always on now, and then you just give it the helper address. In v6 it could be two different commands. First you got to turn on DHCP v6 relay, and second, here's the helper. Some router companies use one command to do everything, relay to this address. So we still have those same functionalities. So the DHCP v6 process is slightly different, but from a client's perspective, it's still going to look just like that if you were looking at it nice and easy. Again, the kind of things that you'd see in a DHCP v4 and a v6 scope, it's almost the same except for the gateway. There's no field. This is not a I don't want to, it's that you can't today put in a default gateway in a DHCP v6 scope. It's not provisioned because it's not designed to be that way. So that kind of gets, especially server folks, a little confused when they're setting up their scopes, because they're asking the network team, okay, give me my address, what ranges do we want to use, what's my mask, and what's my default gateway? And the network guys, you don't need to know that. I'm taking care of that in my router advertisement. And servers like, no, I have a gateway field. No, you don't even have that. Look closer. Right? You don't have that field. That's restating it again as I had done before. Here's a quick little couple of screenshots actually of a Windows 2008 R2 server's DHCP v6 function under its DHCP server. And you can kind of see some assignments here. You can see a little bit down below of the DHCP reply message, and further down in here you can see things like, okay, here's your address, 2001 DB8 lab base : 102, and here is your domain name down here, IPv6 sandbox, and here's your DNS server address. So we see similar things, we just see them in a little bit different naming, a little bit different layout. One of the more interesting things about the v6 world compared to the v4 DHCP functions is that in v4, most DHCP servers keep track of their clients by MAC address, whether they're doing address assignments from a pool or reservations. They know about that device by its MAC address. In a v6 world, that's not the case. It's known by the DUID, the DHCP unique ID, and every client has a unique one. And the DUID number is very, very long. It's not an easy thing. It's self-generated by every client. It has nothing to do with the MAC address. Now, again, like everything else, there's draft RFC where they're trying to change that functionality, but today it's done this way. The challenge is in our cloning. You know, you build the gold master of a client, you test it, it works, and then you lock it, and then you make an image of it, and then you go blast it out to 1,000 computers. So the first computer comes online, gets an address. Computer number 2 comes online, asks for an address, but it's got the same DUID. Different MAC address, different computer, could be a different device, but it comes into the same DUID, and the DHCP v6 server says, well, I just gave you the address. Here it is again. So it assigns computer 2 the same address as computer 1. And then when computer 2 does the DAD, it fails. And because it's supposed to do DHCP, it can't do anything else because it's got the same DUID. So like in a Microsoft world, one of the things you want to do is go through and remove the DUID right before you make your gold master. Now, apparently there's better processes and procedures in different operating systems and some of the VM, the virtual machining OSs and stuff that can do this automatically, remove lots of different things, right? Machine name, DUIDs, and things like that. But it's just something to know. If you're playing with this stuff in a small lab, you're like me, I build one VM, get it set the way I want, then I duplicate it. And then I have to go in and change all the DUIDs so that they're not the same. So it's a little bit different, unique world. If you happen to be playing with v6 addresses, not using DNS at all, but just purely using v6 addresses in applications, they have to know how to interpret the colons now. We got way more colons than we used to. So for v6, you have to bracket, using the square brackets, your address, start to finish, and then everything, the colon afterward could be your port ID. Now, most people don't do this. It's just us, us techs on the back end where we might do things like this. But it's something you have to kind of understand and deal with. So that's a browser. Here's an example of a browser where I went to one of the switches in the Microsoft browser. I think I have another one here using the link local where I had to give it the port name or the interface number. Talked about that percent interface. And here the Internet Explorer didn't like just %11, it wanted %25, which converted it to a percent symbol, and then 11. These are little quirks, but again, this is not your day-to-day use by all your standard users. These are things we do on the back end, and not a lot of necessarily. There's a couple nice add-ons for Firefox and Chrome, especially this particular one. I love it. Down here at the very bottom of this screenshot is this usage of an add-on called Show IP, and it tells you the address that you're going to. So if you go to a v4 address, it shows you the v4. If you're going to a v6 address, it shows you its v6 address. And this is really, really handy, especially in your early days of playing and learning with v6. Another one called IPv4 and IPv6. A v6, you can put it up in your toolbar area and see the same kind of thing, all the different servers and their addresses that they go to. Showing a quick telnet session. This is using TerraTerm. If it's PuTTY, it's pretty much the same. Again, you got to bracket off the address when you're going to it. And then I just did a quick show after I telnetted to it. You can see the client that we came from in that telnet session. TFTP, you can use v6 addressing. This was, again, another interesting thing. It wasn't available until about 3 years ago from the TFTPD application. There's a few others. PuTTY supports it now as well to do TFTP transfers, and there's a couple of other applications. But again, it's just kind of seeing it. RDP, these are some RDP sessions. Now, more interesting, Microsoft doesn't require the brackets to RDP to a v6 client. So that's kind of fun. I would say Microsoft's got the best interpretation of, I know this is a v6 address. You don't have to give me the brackets. Now, if we had a different port number, we weren't going to the standard port for RDP, then you'd have to bracket it, do your colon, and put your port number. So you might have to, but if you're just using RDP Classic, you don't necessarily. Let's see, a little bit about DNS, and you've probably heard about the quad A records as opposed to the A record for v4. And then you have reverse resolution. Again, this is in a Microsoft world. I think I've got an example here for bind. Bind forwards resolution. You can see the quad A record down here. And here's an example that was brought up much earlier about doing the zeros as colons as opposed to compression. It's doing zero compression, but it's dropping down to a single zero per hextet. So that was great. I totally forgot I had that as an example here, so you can see that. Operating systems will treat the IPv6 shorthand notation differently. Some, if you enter it in compressed, will expand it. Some, if you enter it in expanded, it'll compress it. It's okay. It's just you kind of get used to the different ones. v6 reverse resolution and binds notation actually breaks out the v6 address. If you look down here, the pointer record, and into what every 4 bytes dot every 4 bytes. So we still have our 2607 colon F2F8 colon A6D colon 2, but they break it out. We call this nibble notation. Every 4 bytes is a nibble, N-I-B-B-L-E. So you can read up on that. It's relatively easy. I think since bind 9 they've had support for this, so it's not generally much of an issue. One last little bit on security, and I'd like to show a couple screenshots. More than anything else, I want to touch real quick on ICMP. Again, it's required. You can't just categorically turn off ICMP v6 for a v6 world. You've got to leave it on for quite a few different types of traffic. And you still have all the same security issues of DHCP spoofing. Now instead of ARP spoofing, you have neighbor spoofing. You can have router advertisement spoofing. There are some security features that are being implemented more and more by the manufacturers to mitigate that, just like we have in v4. You can still do ACLs, but again, read your router or your switch, layer 3 switch, or your firewall manufacturers to find out what implicit IPv6 rules that they may have, you know, those hidden ones at the end. And really what I want to show right quick, I'm going to go pretty quick to a couple of these, is a lot of people get concerned, well, with scanning, you know, they're going to scan my public network. Well, first off, no, they're probably not going to scan your entire, you know, /64 network. There's too many numbers. But they're going to go, the bad guy scanning utilities are going to go for certain kinds of defaults. They're going to look for certain kinds of things. People are going to implement their v6 to match as close to their v4 addressing world as they can because they know it and it's easy. And we say, don't do that. That's v4 thinking. Change it up. Add some extra characters. You've got a lot of space in your last 64 bits to get creative, but don't put in the common words like I've got foosball, you know, 6 lab foosball in there. Don't do that in a real world implementation. Because there's the hex word dictionaries now that can be scanned very, very quickly. Don't take your v4 address and convert it like I've got there in the last bullet to something easy to understand. Don't do that, because that's what people search or scanning utilities are going to be looking for. So it's just kind of be more creative.
Yeah, so no dead beef cafe then.
Yeah, no dead. You can do that in the lab, right? Yeah, not on your basic everyday network. Certainly not on your public facing. Now, with that said, somebody at some point in time, you could look up Facebook. In fact, let me just do that real quick, because Facebook has it great. All right. So if I ping Facebook, and we look at their resolution of their address, all right, there it is. FACEBOOC, Facebook. But look where it's at, right? It's not in the network. In the first 4 hextets, that's the network. It's down in the interface ID. It's in the 5th and the 6th. But still, it's cute. But yeah, you can do stuff like that. You've seen some of my examples. Those are different lab systems that I've got. So yeah, at least be something creative. Like most people will have their routers at either .1 or .254. Don't do :1 or :254. Make it something more creative. Just a little bit creative even, right? To make it a little bit different.
Okay. Looks like we had a question. Is encryption built into IPv6?
Well, that's going to be a multi-part answer, so let me do it this way. Encryption is built in from the aspect of there are specific field components within a v6 packet to support encrypted bit settings. IPsec is not built into the protocol itself. And then there's 2 things that could be encrypted. One is the addressing functionality, and the second would be the payload. So it was all originally supposed to be mandated to support this in IPv6. It was going to be more secure. And instead they just left it so we've got some fields that support the capability better than what we had in v4. But the manufacturers and the applications are the ones that are going to be required to do it, to actually perform the encryption functions. So from the addressing side, probably about 50–60% of the router vendors will support the encryption of addressing, but there's no client support. The encryption of the payload is going to be left up to the application. So you're still left to, if you want encrypted stuff, putting in some kind of certificate system or SSL or whatever at the application layer. So there are hooks built in to the packet format, but that's where basically it stops. There's nothing else at the protocol that forces it or provides it.
So with the application, not the OS specifically.
Correct. Well, yeah, okay. Yeah. The OS might provide, again, for the addressing piece, but nobody does, and then the application do for the payload piece.
Awesome.
I think we're close. I was going to try to show just a couple of things. There are a couple of attack tools. I'll show that real quick. You'll be able to see it in the recording later on. But these 2 toolkits are very, very awesome. Internally, you would call them your IPv6 security assessment tools. The bad guys call these the hacker tools. Okay, and these things can do very, very dastardly things. Go up on YouTube and search Sam's class IPv6, and you'll come up with some YouTube videos of the gentleman Sam Bowen out at San Francisco City College, where he takes class students in his security classes, and they basically blue screen Windows computers, lock up Macs, lock up Linux. They were doing all kinds of attacks to client operating systems to, quote unquote, prove the point, prove that you could do it with relative ease. But these toolkits are very, very handy for troubleshooting your own real world environment. You want to troubleshoot your own security mitigation. I think that's it. There will be, I'll go ahead and let me bring this back up to full screen just so we have the slides. Wireshark is always your friend from a protocol decode standpoint. A couple of great display filter capabilities, and looking at just specifically IPv6 packets. You can kind of see here, I'm filtering on all DHCPv6 and router advertisements in a particular view. I do this a lot in lab work, looking at very certain things, looking at the packets. A number of different books. More current, last 3 years have provided us quite a few new books in a V6 world. Lots of different information, targeting Windows environments, targeting more Cisco environments. Sylvia Hoggins is just updated her book. Just came out a couple months ago. Another book on security and enterprise. So, yeah, like I say, you kind of look around. There's some more recent material out there. Oh, there's a new book that's just about to come out. It hasn't been fully released yet, but Tom Coffine's talking about address planning, and he really talks deeper about just the addressing. He's not focusing on protocols and everything else. He's focusing on IPv6 addressing content. So all these books are great books. So let me, if I can, show just a couple of things right quick. Some of those tools, there's a number of different websites out there that you can go to that will show if you've got IPv6 running on your devices and what the addresses are. They'll do different kind of functions, do different tests, see what your addresses are, see if your browser's ready to run, see if your DNS is ready. There's just various kind of testing. Quick picture of the DHCP server again here, with a few different addresses, one in a reservation up here, actually the computer I'm on, and then a printer and a couple other Windows computers. And this is, if you notice up here at the kind of the upper left of the screen, I'm RDP'd over IPv6. I'm in a network that's on 1 Charlie 02. This is on one network segment over. And I'm also RDP'd to a computer that's in this lab system. It's on yet a different network. And it's RDP'd over to a network, if you can kind of see real small over there, that's on a completely different environment. My provider, AT&T, does not support IPv6 native yet. So I have tunnels to a couple of different entities, one called Hurricane Electric, known as tunnelbroker.net. And then I also have tunnels to a system called freenet6.net. And so this is, even though these computers are sitting in my lab virtually next to each other, they're literally terminated tunnels in different places. The Hurricane Electric tunnels terminate in Dallas, and my Freenet 6 tunnel terminates in Montreal, Canada. So you can see things like in this screenshot I've got right now. We've got this : 108 address, which happens to be a DHCP. Then I also had the A flag on, which derived these other two addresses, and you can kind of see them here, their public address and the temporary address, all on the same network prefix, but different host IDs. If we look at it from the standpoint of just doing an IP config, you can see all these addresses in here, and it gets really interesting, really quick. About of all these addresses, which one gets used. And so if you can see where my cursor's at on this what's called temporary IPv6 address, I don't have the highlight capability on, one at the very last bit, the 1C61, that's actually the address that'll get used for outbound communications. So you can kind of see over here, let me flip over to the Wireshark, where it did an initial DNS query, and let me stop, come back, I'm back. A little slow on the screen here. It did its initial query, and it used the 1C61 address to go to a DNS server, and then came back. Even though I have all those other addresses, even though I have a DHCP address, it used the address known as temporary, and that is the way it's supposed to be. That's the expected behavior based on the standards. So I'm going to go back to that screen. When you end up with a client with multiple addresses, It could be a good thing and it could be not such a good thing. Remember that the temporary address I'd said earlier could change. So you could actually be doing a Wireshark trace from the temporary to, say, a server, and an hour later you don't see the trace anymore, but the client's still working, and it could be because it generated a new temporary address. And you don't have any way of knowing that till you go back and look at the client. So spend a little bit of time understanding what all that information really translates to. Spend some time in your lab. This is one of those things that you pretty much have to work with in the lab environment to really understand what you've got and what it can do. I've really taken up a lot of time, and I very much appreciate everybody hanging in there with me. Do we have any other questions?
Looked like there was two. Curious what Jeffrey's seeing for adoption rates for IPv6 implementation in company lands that don't suffer from things like IPv4 address shortages.
Well, the whole v6 deployment implementation is still moving pretty slow. The areas that it has certainly picked up is where v6 addresses are depleted from the regional internet registry, the RRs. Like Aaron has said, we've got less than a /8 left in their pool. Now, just when they run out doesn't mean that all the v4 stuff goes away and it's going to stop working. But it does mean in those certain areas, and Asia Pacific is the most common, that even the providers can't get v4 addresses anymore, and they're running out quickly. So there is starting to become environments that have v6 only. They're starting to become, probably in North America, more companies that do business internationally, especially, that are having to at least also add v6. And we'll call that dual stack. I don't think we're going to see in years where we'll turn off v4 and be v6 only. I think we will be dual stacked for a long time. There are ways, and I actually have a test network set up that is v6 only, and you end up implementing what's called NAT 6.4, DNS 6.4, and it's a two-stage function between a router and a DNS that you're v6 only. You ask a question, and your DNS goes, well, I'm v4 connected, so I'm going to re-ask the question and go find that entity's v4 address, and then I'm going to convert it to a special v6 address to give back to you. And then you have a router that takes that special address and converts it back to a v4. So I think the implementation is starting to occur. I think more people are starting to play with it in lab. Maybe some of their forward-facing content, they're doing dual stack. As far as internal network stuff, that adoption is still a little bit slower because you still have to do a tremendous amount of research to find out everything that really is on the network and what can support v6. So we're getting there. Hopefully things like our podcast here and other presentations that are out there and some of the more recent published material, people are starting to work through it and play with it and learn it and then be ready to start that deployment. So it's still moving a little slow, but I think it's creeping up in popularity.
I think the last question is, how many times can a path transmit a packet too big respond back to the source?
How many times?
Yeah, so how many times can a router or so transmit a packet too big response, like a fragmentation response or so?
It'll just do it once. Oh, well,
Okay.
I guess I'd have to say it does it on every packet that comes in that's too big.
Okay, so if a router 3 hops in, says packet's too big, and the source sends it back again, but it's still too big, like is there something in that message that says this is my acceptable size?
Yeah. I thought I said that, but yes, in the packet too big message is a field that says, here is my MTU size. So there should never be that functionality. If a router 3 hops down says, again, kind of like my example, I'm 1300 byte MTU, your packet's 1500 byte. Okay, source, here's your packet too big message, and here is the MTU that you need to set to. And if the client OS does not act on that correctly, then the router would keep sending message back. But generally, it should be a single message.
Okay. And so, say router 1 says say each router in the path has a different MTU size, each one in decreasing. We're really going a contrived scenario here, right?
Yeah. So 1500, 1400, 1300. So yeah. Exactly. Every router would have to do its bit. Exactly. And so the point I wanted to make, and maybe there's some protections built in, is that would seem like a really interesting avenue for a denial of service attack. Is you send a packet that you know is going to be too big, but you spoof the source address, so when the message too big message goes back out, it goes somewhere else. Yeah.
And so you have the routers turn around and do some pretty nasty things on your behalf.
Yeah. It's true.
Okay. So there are no protections built in to date then?
Not for that. Not really. I mean, about the only... I'm not even sure what the protection on that would be specifically. How you would protect against that. Yeah, that's a different kind of a spoof attack. I'm not sure how that protection would be.
It's similar to a number of the current denial of service attacks, and basically you have to get into some like packet inspection and thresholds and so on, and it gets nasty. But we're here at 9:15. I think you're about all wrapped up. I don't think we have any additional questions coming in. I want to thank you so much for coming on. I've like a lot of people, I've been putting off learning about IPv6, and I've learned more in the last. My call counter says 2 hours. I've learned more in the last 2 hours than I've learned to date on IPv6. So thank you so much.
Well, my pleasure. Let's see. I'll throw up for the last bit. You had my Twitter link up there, I believe. So I'll put it up here real quick again for folks that they want to see. There's also an email contact. Questions are always try to answer as best I can. If it gets to be too much, then we'll kind of go a different avenue. But I'm always willing to help. Like I say, it's one of the things I think from a technological viewpoint, it's going to be the coolest thing we have. Everything else is just network speed, way cool virtualization stuff, and all this, cloud and SDN and things like that. Yeah, but the underlying protocol is going to be required for all of this new stuff to work well. So I think more people that get to it, learn it. I'm actually doing some hands-on labs, build your own lab, small, very, very, very low investment, like $5-10 investment to build your own lab, to do real routing at the North American v6 Summit in Denver in a few weeks. And
okay. Well, I'll tell you what. I really kind of want to have you come. I kind of want to have you come back on the brown bag and do that one for us as well. Then.
Well, we could.
If you don't mind.
No, I mentioned interest in that. I had another presentation I'm doing for a couple of entities next month on IPv6 in Wireshark. Kind of focusing a little bit about using Wireshark in a v6 world. The different filters and ways to look at things and trying to understand the protocol with the packet decode. So I've got all kinds of things we can do.
Alrighty. Well, with that, I'm going to go ahead